to produce the food that goes on our plate. The food sector uses half of all the land we use on the planet. It uses 2/3, 3/4 of all the water we use on the planet. It's incredible. And it's the second or third biggest emitter of greenhouse gases. So the impacts are higher than any other sector in total. This means that we have to change.
As the world's population has increased, so too have the demands on our limited food and water supplies. Scientists are spending sleepless nights trying to find solutions to these challenges. Equipped with knowledge, expertise, passion, and hope, they are supported by an institution that believes that science can help us save our planet.
The challenges of feeding the 10 billion that we expect to be on the planet before very long are immense. We have to find ways of generating food that is of good nutritional value for all of those people.
Ryan Lefers and Professor Mark Tester have come together to take on this task under their startup, Red Sea Farms.
Red Sea Farms is a startup from KAUST. We do our research in the university like academics. And what's special about here is that it really does provide an environment that's highly supportive of research, discoveries into impact.
Generally, we have technologies that fall into 3 main buckets, and then they're all connected by a central system. So bucket 1 is the plant science.
A kilogram of tomatoes, that's like 4 large tomatoes. That requires about 350 litres of water to produce. Just a small bag of tomatoes. It's extraordinary. And the thing which we've done, which I think is quite good and potentially very impactful, is to just use less fresh water and substitute it with salty water. So we're trying to unlock the massive reserves of salty water in the planet that we currently do not use for our food production. So we try to not use 350 litres, but maybe 20 or 30 litres of water to produce that kilogram of tomatoes. A little benefit for us humans, though, is that when you grow the plants in brackish water, the fruits taste fantastic. They accumulate more sugar and taste sweeter. They're slightly more acidic as well. And they're actually also better for you, because when the plants get a little bit stressed, they want to produce antioxidants to help stay healthier for longer. And what's the main antioxidant? It's vitamin C.
And then the next bucket is the active cooling bucket. So in this climate, it gets hot. We need to cool the controlled environment. And so we've got a number of technologies that are patented around how we can do that in a sustainable way, and especially connected with solar energy.
When you're in this hot, dry environment in the Middle East, a huge amount of water is used to cool the greenhouse. And so this was Ryan's technology, where you simply substitute fresh water for salty water to cool the greenhouse. And immediately you are reducing the freshwater consumption by a factor of 10.
Let me walk you through some of the active cooling pieces, which are right over here. So behind door number 1 here is actually the first of our active cooling systems. This is simply a saltwater-based, in this case seawater, but saltwater-based evaporative cooler. And what's different about the system is we've got sensors built into the system to control it and to protect the cooling system. Door number 2 behind me, this is door number 2. This is actually, it's a humidity capture and reuse system. So we call it HumCap for short. But the HumCap system allows us to capture humidity that's exiting the greenhouse, and then we can recycle that back to the front end of the greenhouse to reuse it for cooling. So this allows us to save a lot of the water that we would otherwise evaporate, so like 50, 60, 70% depending on the climate, from the HumCap. The other thing that's interesting about this is it's a liquid desiccant-based system that allows for air purification. So we can purify the air of things like viruses and bacteria, pathogens. So one of the things that with the solar roof is it's actually capturing that infrared light. It's preventing it from going into the greenhouse. It's converting it to energy, electricity, which powers that mechanical chiller, which then is connected directly to our stored thermal tank of liquid desiccant. So then we use that at night. So it's the sun powering this whole system, but it's actually the spectrum of the sun that we don't use when we're growing crops, and in fact, which is detrimental to the system. So we're taking something that would otherwise be a negative to the system and using it as a positive. And then the third bucket is around passive cooling. So this is like the heat blocking, which is what the sensors and the control system is pulling this all together in this beautiful system that you see behind me. So the photovoltaics are direct connected to the fan, which is a good thing because as the solar energy goes up and we get more power out of our photovoltaic panels, we need more fan energy to actually cool the greenhouse and move the heat out quicker. So it's directly correlated. And then I want to show you the next system, which is our Cortex system. What's interesting about the Cortex system is that we've built this all in-house and we've made this for this environment. Which is different from like the northern climates where greenhouses originated.
This is one of our products. We call it the environmental sensor. So what lives inside this enclosure is this little sensor, which measures quite a lot of things. It measures temperature, relative humidity, pressure, and CO2 levels. We have another sensor. We called it the water sensor. It's specifically designed to monitor the root zone inside the plant. We also use that sensor to measure the water salinity content in the water cooling system. All of the data we get here are integrated into the cloud, so we could access this data at any time, anywhere in the world.
But we're actually really using the systems, the technologies as a whole, as a package. We can grow maybe 100 different varieties of fruits and vegetables. These are capsicums, sweet peppers. They're only 6 weeks old, but they're already starting to produce some fruits. So we've got different colors. Different colors are generated very simply, but us humans like it. It's visually appealing. But for me, the key thing is the fact that we're reducing this freshwater footprint for producing these food. So your bag of capsicums, instead of taking 300 litres of water, will only be taking about 20 or 30 litres of water for their production. That's impact. The combination of digital technologies and biotechnologies gives us huge opportunities to really reduce that environmental impact of our food production, increase that sustainability, because we need to do it. There's a will to do it, and I think there is a way to do it as well.
Professor Rod Wing trails the big question on how to feed 10 billion people with another big question.
How can we sustainably feed the world without destroying our planet? I wake up every morning thinking about this, and it's a daunting task, but we do have solutions that are sustainable.
A daunting task indeed, but Rod has a number of potential solutions.
Hey, everybody. How you guys doing? All right, this is one of our greenhouses. This is where I do some of my experiments, primarily on the wild relatives of rice. Right here, we're looking at a plant called Rhiza cortata. This is a wild relative of rice that can grow in salt water. Rice is one of the most important food crops in the world, and it feeds half the population. And as you can see, it has a flower. This is pollen anthers coming out right now. It's pollinating, and this is its panicle. It has 20 to 30 seeds on every panicle right here, which is really not enough to be a staple crop at the moment. But what we want to do is try to domesticate this plant. And one of our targets is to make the Rhiza cortata so it doesn't shatter. So now it keeps the seed on. Then we try to improve the yield. And eventually we would be able to grow this plant along coastlines where there's brackish water, and it could produce somewhere between 3 to 5 tons per hectare, which would be a fantastic contribution to growing rice without dwindling our fresh water supply. So that's one of the big things we're working on.
Biotechnology and plant genetics offer solutions that can address the need for food in some of the less fertile areas of the planet. One KAUST professor draws on personal experience from living in these regions.
I love dates since I was a kid. Whenever I find a date, I will eat it. One weekend, I was sitting at home and I said, why don't I study them?
Meet Ikram, who transformed her passion into a career that might help crack the 10 billion challenge.
Date palm is one of the most beautiful plants in the world, in my opinion. It exists since more than 4,000 years. I think this is a plant with personality. It has a very strong personality because it's very resilient. Date palm is a good example to study plant adaptation to desert conditions because of their great root system. Their system is very complex. I call it a great hydraulic system. So they can form roots that grow laterally, so at the superficie, so that allows it to uptake water quickly when there is high moisture or when there is occasional rainfall. They also develop very deep roots, seeking the water. The shoot is very interesting because it has great ability to resist high temperature. So they start flowering around 25-30 degrees. The fruits mature at 60-55 degrees. So usually the date palm harvest is in August, July, where it's the highest temperature in the kingdom.
If date palms are so perfect, what is Ikram's quest then?
The saying is, the one who plants the seeds, it doesn't eat the fruit. That's how slow the date grows. So what we are doing now is we try to optimize the transformation protocol. So the protocol is already established, which is good. What we want now is to take advantage of this established protocol to accelerate the growth, using either a foreign DNA or using a metabolite or using a microbe that can help make the plant grow faster. That will help us to create the fast palm. Then to make them fit, then we will have to wait a little bit until we can see whatever we have introduced does not perturb the structure of the plant and test that is really making the plant more resistant.
Similar to Red Sea farms, several experiments require researchers from different disciplines to collaborate.
The beauty of this place is very interdisciplinary. For instance, I have collaboration not only with people working with plant, but also working with electrical engineering. For instance, the sensor lab. The sensor lab has nothing to do with plants. They don't work with biology or root or developmental biology, but they are developing sensor to detect abiotic stress or detect hormones.
Or detect an invasive species that threatens millions of date palms and coconut trees around the world.
There's a problem here with something called red palm weevils. It's basically like a little snout beetle that can lay between 200 to 300 eggs that develops into fairly big fat grubs that lives inside the date palms. And they basically eat the interior of those date palms, ferment the interior until those date palms or the trunks are basically all hollow. So if you get a windy day, they might completely fall over, and that's obviously affecting the yield of those date palms. So we are trying to detect which ones are infested and which ones are healthy, and we're using drones and various types of cameras to do that. It's quite a significant problem. It started about 20 years ago here in the Middle East, but it's really spread, and it's costing the industry a lot of money every year. There's a lot of wasted resources going towards this. There's a lot of yield that's lost because of outbreaks in certain areas, and this date palm farm in particular has some issues with red palm weevils.
We've seen Boon Uy in the previous episode helping the Red Sea team with connectivity through underwater internet. This time, Boon has a different innovation for detecting red palm weevils.
We solve this problem by using a single optical fiber. We are using a standard optical fiber that we're using for the detections. Other technology, usually is very time-consuming. You need to be the so-called invasive. You have to drill a hole, put in a microphone, and listen to the sound of lava. As for our technology, we can do it in real time, 24/7, and can be widely deployed because we can detect up to 1,000 trees by using a 10 kilometers fiber and one single sensor box that we built. If this problem goes without control, then it will lead to a disaster. A tree usually be able to survive up to about 40, 50 years, but during the peak production time, at about 20 years or so, and being destroyed means that you have to grow the tree and wait for another 10 to 20 years before they can produce again. That's actually damaging the economy significantly.
Growing economies face many challenges. One of the truly daunting ones is water scarcity, especially when these economies are in arid regions where evaporation levels are higher than rainfall. Around 90% of clean water is discharged through flushing toilets, irrigation, and industrial use. Could wastewater recycling be a good solution? Let's ask the experts.
My main goal is to really challenge the way that we are seeing wastewater as a waste and not as a resource, and perhaps eliminates the definition of wastewater and just say that it is water.
The existing problem with the conventional wastewater treatment plant, it's an energy-intensive process, and 50% of this energy goes for aerating the system. Again, you need to provide oxygen for the organisms to grow. And at the same time, we don't recover any of the valuable resources.
French chemist de Lavoisier stated, "Nothing is lost, everything is transformed." Now, Peiying and Pascal are proving that assertion.
With the conventional activated sludge process, we only treat the wastewater and we dispose it. With this system, we can treat the wastewater, and at the same time, we can recover green energy as hydrogen. And if we capture most of this energy, we can convert the whole process to become an energy-neutral process. We call it anaerobic electrochemical membrane bioreactor. The concept behind this biotechnology is that you have a certain type of microorganisms that they like to grow using electrodes as their electron acceptor. For example, we as humans, we use oxygen to respire. These organisms, they like to respire using an electrode material. So what happens here is that in wastewater, you have certain organic compounds. So these organisms, they survive on these organic compounds. So they break down these organic compounds and they capture the electrons and they transfer these electrons to the surface of an electrode. So the electrons then move to another electrode we call the cathode, where hydrogen is generated. So at the cathode side, we have a certain type of catalyst that helps the production of hydrogen. So the electrons and the protons that are generated from the oxidations of organics in wastewater, at the cathode, they are converted to hydrogen gas. So in this first unit, we have these electrodes, we call them the anodes, and this is basically what it is. So this is where the microorganisms, they grow on the surface as a biofilm. And in addition to the anode, we have another type of electrode, we call it the cathode, and this is basically, it's made of nickel. This is where the hydrogen evolution takes place. In addition to that, as I mentioned, you're producing the hydrogen, you have a gas bag at the top, this is where we capture the hydrogen. And the water from the top of the first tank goes to the second tank, where you have these membranes where you filter the water. So you have a certain pore size of these membranes where it allows only the water to pass through, but not the microorganisms. And then you can produce a type of water that is suitable for reuse. And here I'm just going to open this just to show you how we're producing real water.
From what you see over here, we are right now at the wastewater treatment plant. We are here with our anaerobic membrane bioreactor prototype to demonstrate the next generation of treating and cleaning our wastewater. What we hope to do is to have a decentralized way of treating wastewater and harvesting the energy that's present in the wastewater and converting them into methane energy, which can then be converted into electrical energy. And by doing so, we can make use of the energy that is contained within the wastewater to finance the entire operation of cleaning our wastewater, with the end product of a high-quality reclaimed water that can be used for other non-portable reuse purposes, such as for food production, as well as to enhance livability by growing green landscapes in the urban environment. The wastewater from Modon is coming through the pipes that enters into the equalization tank. The equalization tank serves to equilibrate the flow rate so that it can go into our anaerobic membrane bioreactor, which is the taller structure that you see at the background. Inside the anaerobic membrane bioreactor, we have anaerobic microorganisms that are tasked to convert the organic carbon into methane. So the supernatant then goes into the membrane filtration tank, and this membrane filtration serves as an additional physical removal process to remove the particulates that may be present in the wastewater to get better effluent quality. This effluent then goes into a disinfection process, which is the UV reactor that you see at the back. So together with hydrogen peroxide as a chemical disinfectant, we have a UV hydrogen peroxide-based disinfection to serve as a final disinfecting of the clean wastewater. The clean wastewater then goes into a final polishing step, which is through the activated carbon column over here. And by then, we expect that the wastewater will be of very high quality that can be used for other purposes, such as for landscaping irrigation or maybe even for food production. Decentralization is one of our key objectives to demonstrate for our future generation of wastewater treatment processes, because we do believe that this is the way to go as cities expand and new cities get developed. Decentralized treatment makes more sense than centralized wastewater treatment processes because it will require less energy to transport all the wastewater from multiple different households to a decentralized wastewater treatment process.
The success stories on the KAUST campus are legion, along with the dozens of world-class startups and entrepreneurship opportunities. Most importantly, these all focus on making the world a better place. In the next episode, we'll explore more of these groundbreaking, life-saving startups that feed and sustain our world.